By nature, black holes do not themselves emit any electromagnetic radiation other than the hypothetical Hawking radiation. So astrophysicists searching for black holes must generally rely on indirect observations. For example, a black hole's existence can sometimes be inferred by observing its gravitational influence on its surroundings. On 10 April 2019, an image was released of a black hole, which is seen magnified because the light paths near the event horizon are highly bent. The dark shadow in the middle results from light paths absorbed by the black hole. The image is in false color, as the detected light halo in this image is not in the visible spectrum, but radio waves. Quote, the Event Horizon Telescope, EHT, is an active program that directly observes the immediate environment of black holes' event horizons, such as the black hole at the center of the Milky Way. In April 2017, EHT began observing the black hole at the center of Messier 87. In all, 8 radio observatories on 6 mountains and 4 continents observed the galaxy in Virgo on and off for 10 days in April 2017, to provide the data yielding the image in April 2019. After 2 years of data processing, EHT released the first direct image of a black hole. Specifically, the supermassive black hole that lies in the center of the aforementioned galaxy. What is visible is not the black hole, which shows as black because of the loss of all light within this dark region. Instead, it is the gases at the edge of the event horizon, displayed as orange or red, that define the black hole. On 12 May 2022, the EHT released the first image of Sagittarius A*, the supermassive black hole at the center of the Milky Way galaxy. The published image displayed the same ring-like structure and circular shadow as seen in the M87 black hole, and the image was created using the same techniques as for the M87 black hole. However, the imaging process for Sagittarius A*, which is more than 1,000 times smaller and less massive than M87, was significantly more complex because of the instability of its surroundings. The image of Sagittarius A was also partially blurred by turbulent plasma on the way to the galactic center, an effect which prevents resolution of the image at longer wavelengths. The brightening of this material in the bottom half of the processed EHT image is thought to be caused by Doppler beaming, whereby material approaching the viewer at relativistic speeds is perceived as brighter than material moving away. In the case of a black hole, this phenomenon implies that the visible material is rotating at relativistic speeds greater than 1,000 km per second, 2,200,000 miles per hour. The only speeds at which it is possible to centrifugally balance the immense gravitational attraction of the singularity, and thereby remain in orbit above the event horizon. This configuration of bright material implies that the EHT observed M87 from a perspective catching the black hole's accretion disk nearly edge-on, as the whole system rotated clockwise. However, the extreme gravitational lensing associated with black holes produces the illusion of a perspective that sees the accretion disk from above. In reality, most of the ring in the EHT image was created when the light emitted by the far side of the accretion disk bent around the black hole's gravity well and escaped, meaning that most of the possible perspectives on M87 can see the entire disk, even that directly behind the shadow. In 2015, the EHT detected magnetic fields just outside the event horizon of Sagittarius A*, and even discerned some of their properties. The field lines that pass through the accretion disk were a complex mixture of ordered and tangled. Theoretical studies of black holes had predicted the existence of magnetic fields. In April 2023, an image of the shadow of the Messier 87 black hole and the related high-energy jet viewed together for the first time, was presented.